Hello everyone, welcome to NPTEL's Introduction to Semiconductor Devices course. So we are in the first week of the live session. I am Om Maheshwari. I am a PhD scholar at IIT Gandhinagar and I will be working with you guys throughout this course to help you solve different questions and understand any concepts that you find difficult. So this course is offered by Professor Naresh Kumar Imani from IIT Hyderabad. So I hope you guys must have seen his videos. And so, if we look at the content of this course, we'll be looking at a wide variety of topics, starting from the basics of semiconductors, semiconductor materials, and properties, till PN junctions, diodes, MOS capacitors, MOS transistors, and the short channel effects in MOS transistors, and the optoelectronics and light emitting diodes. So, we'll be covering a variety of topics. So, before this course, it is important that you watch the videos by Professor Naresh, and they will be very, very helpful for you throughout this course, as well as if you want to take your exam for this course, that those videos will be very helpful and may help you uh, in your colleges and future projects also. So try to watch those videos every time before you come uh, for these live sessions, so that we can have a more meaningful discussion and can you can ask your queries here anytime. So, in case you want to reach out to me apart from these live sessions, here is my email ID. Please feel free to send me an email if you feel any doubt or you want any other consultation regarding this course. And uh, yeah, so there are two more TAs for this course, and you can like reach out to them also. Okay, so now let's start this course. Please feel free to type in the chat box or raise your hand whenever you have any query. We can revisit any question any number of times. So keep it interactive and we will see how it goes. Okay, so let us start. So the first question is, so all these questions are based on your week 1's video lectures and they are pretty easy questions. Should be able to solve them if you have watched the videos and they will help with your current assignment also. The first question is, according to de Broglie's hypothesis, all matter exhibits wave-like behavior. Among the following particles, which have the smallest wavelength associated with it for the same velocity? So this is a very easy question. So can anyone answer it? You can write it in the chat, or if you want to speak, you can unmute and speak also.
Cricket ball, sir.
Yeah, cricket ball. Okay. So can anyone like tell in one line what is the de Broglie's hypothesis?
Yeah, so this is Sushant.
Hi,
This
Sachin.
de Broglie hypothesis, lambda is equal to h upon v. So v is basically the momentum. So to have the smallest wavelength, one should have the largest momentum. So momentum would be highest, largest for this cricket ball.
Right, sure. Okay. So So we are seeing a lot of new things here in this question. First is de Broglie's hypothesis, which is simply matter exhibits wave-like behavior. So what does this mean is like there are like probability waves associated with every particle or every matter. So and this wave-like behavior has a wavelength associated with it, and this wavelength is lambda is h upon p or h upon mv. P is the momentum, h is the Planck's constant, m is the mass, and v is the velocity. Okay, so the question says which among the following will have the smallest wavelength associated with it for the same velocity. So we have lambda equals to h upon mv. So if you see mass of let's say electron is 9.1 into 10 to the power minus 31 kg, right? And mass of proton is around 10 to the power minus 27 kg. Mass of alpha particle, it should be in the similar range. I'm not exactly sure, maybe 10 to the power minus 25 to 27 kg. But cricket ball, it would be at least like, I don't know, 100, 150 grams. The smallest ball would have that, or maybe let's say 200 grams, right? So the mass of the cricket ball is enormously high, and for Planck's constant is a constant, velocity is same, so lambda will be lowest for highest mass, which is cricket ball. Okay, so let us assume the velocity to be, let's say, 1000 meter per second. Can anyone tell me what is the lambda for this cricket ball? If m is 200 grams. Take a minute, try to solve this. You want to know Planck's constant? Planck's constant h is 6.626 into 10 to the power minus 34 joules. Okay. How to find it? H upon mv. H is 6.626 10 to the power minus 31 upon cricket ball's mass is 200 gram, that is zero point 0.2 kg. Velocity is 1000 meter per second. So we should get something like
You are
3.3.
getting
Sorry,
3.3 into 10 to the power minus 36.
sure.
3.13
So
into
3.31,
10
right?
to the power minus 35.
Okay.
Uh,
10 raised to the power minus 32, sir.
Sorry, it is 34 for
Minus
Planck's constant.
36.
It should be minus 36 meters. Is there any doubt in this? So Planck's constant is 6.626 into 10 to the power minus 34. Our ball's mass is 0.2 kg and 1000 meter per second is the wavelength. Right,
Right, getting the same answer. Yes.
sure. Okay, so quite a few things to like learn from this is it is very important first of all to like be very mindful of the units, right? Because in all of these questions and many more numericals that you have, right, uh, there are several ways to express different quantities. There are several different units. So it is very important to be very mindful like what units are you using. So with the standard flex constant, you should use kg and meter per second. If you want to use something else, you need to change this constants value also according to the required units. Okay, so let us move on to the next question. Consider an electron moving in a circular orbit around a nucleus. If the radius of the orbit is halved, how does the de Broglie wavelength of the electron change? Okay, Harshvardhan says it doubles. Uh, do you all agree with him? Okay, so those who all say double react with thumbs up. Those who say no, it's not double react with thumbs down. Harshvardhan and Adi say the double. Okay, other people don't know or they don't have an opinion on this question. Sushant says it doubles. Okay, so all of you are saying it doubles. Let's see. So one thing to like, let's talk about it a bit. So we have a nucleus, right? Like this, and we have certain orbits around it where the electron can be, right? So electron can be here or in any other orbit. But one thing is for sure, it should be in a very predefined orbit. It cannot exist, let's say somewhere here. It has to exist in these predefined orbits only, right? So the energy the energy levels occupied by electrons orbiting around the nucleus are quantified. What does quantified mean? Quantified means it's like it's not continuous. It's like some fixed energy level, some discrete energy levels are only allowed. Right? So it cannot exist anywhere. It has to exist in these fixed energy levels. And how these fixed energy levels are found, you can find it this relation to pi r is n lambda. This is also again a derivative of uh, de Broglie's hypothesis. So these fixed levels or the distance, fixed distance from this radius from this nucleus r should be an integer multiple of the wavelength and is an integer. Okay, so the question now says the radius is halved if r changes to r by 2. What will happen to lambda? It will halve, right? If r changes to r by 2, then according to this relation, lambda will also change to lambda by 2. So answer is,
But what will happen to this factor n, integer n?
yeah, that's a good question. So n must be such that it is an allowed level, right? N could be, let's say, 4, but when it's halved, it changes to, let's say, in the second state. Let's say it is coming from here till here, second from second to first one, then it's allowed.
All right.
But if it's already at first one and you are trying to halve it, then no, that transition will not be allowed. That transition will not take place. Or you cannot go from third to somewhere in between 1.5. That is also not possible. Either it will go to the second state or in the first state, right? So this definitely needs to be taken care of. Only integer values
But
are
that is
allowed.
not mentioned in the question. This n part is not mentioned in the question. So it is to be assumed.
No, this is a standard law. This is not a assumption.
Okay.
Yeah. So if you watch the, I
Okay.
think first or second video, this would be more clear.
Okay.
Okay. So is there any doubt in this question?
Lambda means lambda tends to R by 2.
Sorry.
Lambda means
Lambda is the de Broglie's
uh,
wavelength, which we just saw here, right?
Yes, sir. Answer will be half, sir.
Yes. Okay, so maybe let's take a hypothetical case. Let's say this is the nucleus and electron is in the first orbit, right? So, so this is just R. Now, what you want to do is you want to change this R to, let's say, R by 2. So, first question is like, can we do that? Okay, science says yes. Sushant, you can you answer this? I think there was some confusion regarding this, right?
I think no.
Right. So
I'm not
let's.
sure.
So what is lambda? Lambda is h upon mv, right? You cannot change h, you cannot change m, right? But let us say for the same lambda, let's say if you are for a fixed lambda, you cannot do this transition. That's not possible. But let's say you were to increase the velocity to change this lambda, then this transition could be possible. Does this make sense, Sushant?
Yes.
Right. Yes.
Okay, so
Sir,
for
I
yeah,
sir, I have a doubt that
yes,
either if we change the orbital size, doesn't it will fall into the nucleus due to the intermolecular force?
okay. No. So answer is no. It does not fall into the nucleus due to the intermolecular. What is intermolecular force, first of all?
Ah, sorry, interatomic force. Uh, the,
Okay, so your question is why does the electron not fall into the nucleus, right? Can anyone answer this?
It is, sir, moving to
What? Sorry.
Jupiter moving and uh,
सर वो स्पेसिफिक ऑर्बिट्स में होते हैं जो नील बोर ने वो दिया था.
Yeah, that is correct. So okay. So what uh, you are thinking like it's a very again classical picture. It should like due to the force of attraction, it should fall in the into the nucleus. But what Niels Bohr and de Broglie, what they all found that they cannot even exist anywhere in these regions. Right? This is the results of their study of the quantum physics. They cannot exist there. They can only exist in these orbitals or nowhere. For it to fall into the nucleus, that is like quantum mechanically not allowed. But there's no like classical analogy for this, like why it does not fall into the nucleus. It's maybe you can think of centripetal force, but that is actually not true. It's just something in quantum mechanics related to it. It cannot be explained by classical physics.
Yes, sir.
Hello.
Yes.
This reducing
So,
this radius
sir,
by half would still be a new
What? Sorry.
orbit. The half radius would still be a new orbit. So why would it fall into the nucleus?
Yeah, we are not saying it will fall in the nucleus. It was a different question.
Right.
Yeah.
sir, would the hybridization of
So
the electron or the that specific element matters in this aspect, sir?
Hybridization.
Or
Uh,
the number of electrons in the outer layer of that specific element, would it matter in this aspect, sir?
would matter in what exactly? What is your question? Matter in what?
Like, is it related to anything of the number of electrons in the outer layer or the hybridization like sp2 or something like that?
Okay, so hybridization only comes uh, into picture when we are talking about molecules, right? It does not matter in atoms. In singular
Okay, sir.
atoms, hybridization is not important, right? So, and other your other part of the question is like, does this like matter with the number of electrons? No, because this is again a standard rule. No matter the number of atoms, or sorry, number of electrons, they will always take these fixed quantified uh, radiuses.
Yes, sir.
But yeah, their position may change according to the different, like whatever different number of protons and neutrons in the nucleus. Definitely, this R will not be same. R equal to like whatever R is. Let's say for hydrogen atom will not be same for R in let's say some oxygen atom, right? That R will be different. But there will be the same fixed states that is always holding true. The law is true, but yeah, this value of R may change.
Okay, sir. Thank you.
Okay. So anything else in this question?
no, understood.
Sorry, is there a question? If the length of the
No, sir.
potential wheel is changed, this is possible. Potential well is changed. What is possible if the potential value is changed? Yes, exactly. So even when the okay, so we have not discussed about it yet, but you may have seen the video, right? There is, I think, something related to Schrodinger equation and finite and infinite potential wells. So if you change the potential energy, the uh, okay, so let me just put it here. Let's say this is a finite potential well. This is the potential U. Now, if you are changing this potential energy or you're changing this length, your energy states would change. But again, they would still remain quantized. They will not never become continuous. These energy values will change. Definitely E1 value and E2 value, their values will change, but they will still be quantized. Okay, so let's not confuse ourselves further. And the whole takeaway here is that is maybe this that the energy around orbit is quantized. do not quantize. And this is the relation that is important here. So let's not digress further. Let us see the next question. Okay, the wave function of a particle moving in free space is given by this. The energy of the particle is.
So option C.
Okay, option C, did you say?
Option C, sir. A square k square by 2n.
Okay, option B. Are there any other answers? Okay, Sushant agrees with B. Other people? Okay, so option B is correct. Let's see where it comes from. So you must have read about the Schrodinger's equation till now, hopefully. So what is Schrodinger's equation? Or I would say time independent Schrodinger's equation to be precise, when x cross square by 2n del 2 psi by del x square plus bx psi equals to e psi. So here, this is the Schrodinger's equation. So what it tells you the relationship between the energy, the potential, sorry, the potential and the wave function. Wave function is psi. So for a free electron, which is given in the question, the particle is, sorry, free particle is free for moving freely in free space. So for a free particle, V of x is 0. There is no external potential stopping it. So your equation becomes minus h cross square by 2m del 2 psi by del x square equals to E psi. If I rearrange this, del 2 psi by del x square plus 2mp upon h cross square equals to 0. Or I can leave psi, yeah, psi here. Okay, so let me call this k equals to 2me upon h cross square, or e equals to h cross square k square by 2n. Okay, so this is true.
K
Sorry,
square equal to 2, K square equal to 2 by h square.
Sanjeev, your voice is not audible. Can you please type your query in chat?
Sir, K square equal to 2 by h square.
Yeah, sorry, k square equals to 2me by x square. Yeah, you're correct. Should be k square, not k. The wave function does not represent a periodic wave. Okay, why does it have to be a periodic wave? What do you mean that it is not a periodic wave?
Sir, K is constant, sir.
Yeah,
Oh, not periodical.
sorry.
So not periodically. If K is
K
constant.
K is K is uh, like a representation of your momentum itself, right? Uh, K is related to momentum. So it will not be constant. K is not constant. It will change with energy.
Yes, sir.
Akela, I am not able to understand your question. Uh, Wave function does not represent a periodic wave. Uh, I think it is a periodic, you can say in terms of x. If you say, what is e to the power I kx? E to the power I kx is, I think, cos kx plus I sin kx, right? If I'm not wrong. Let me check.
Yes, sir.
Plus you add another 4 e to the power ik minus I kx, which is 4 maybe cos kx minus I sin kx. Whatever, I may be like incorrect about these signs, maybe. Like I don't know if it's minus here or here, whatever it is, but it is again in like only cos and sine terms. So what do you mean like non-periodic? And why is that important in this context? That I'm not sure. Sahil is asking, is there another session from 6 to 8? Okay. Sahil, I'm not sure. They could be the same questions. I'm not sure. So if you do have time, you can attend that one also. But if not, you can totally skip it. It's fine.
Excuse me, sir.
Yes.
Sir, when we'll do psi square, then we'll get some imaginary part and some real part of
Okay.
this equation. Sir, what exactly does the imaginary part represent? Because psi square makes the probability. So, in the probability, the imaginary part does not make sense.
Okay. So what we do is we do while finding the probability is psi star psi, right? Mod psi star psi, or yeah. So
Okay,
for
we'll
this
take the
psi,
mod, so
yeah,
that I
we'll
forgot.
not even mod. Even if you don't do the mod, this is like you see, forget about the mod. This is psi star psi, right? This is conjugate of psi. Whenever there is a conjugate, this will be a real number.
Yes, sir.
Let's say it is like e to the power I kx dot e to the power minus I kx. This is the conjugate. This will be a real number. For here, it will be 0. Oh, sorry, 1. E to the power 0 is 1. Conjugate, when you multiply a imagine, or I would say a complex number by its conjugate, you will get a real number.
Yes, sir.
Okay, so okay, so Michaela, again, I don't understand this question. Function given a solution point. Which function and which solution point are we talking about? Okay, so I just read through the requirements for the wave function. It has to be continuous. It has to be differentiable. It should be single valued. That means it should not have different y values for same x value. But there's no requirement for it to be periodic. Periodicity is not a requirement. Yeah, wave function is a solution of the Schrodinger equation. Okay. Is there any other doubt in this question?
No, but this
What?
Schrodinger equation does not say it need not be it need to be periodic.
Yeah.
So the previous question,
Mhm.
uh, it's not sure whether it needs to be periodic all the time. Rather, it does not say anything.
Hmm.
It can be plain at the most, but it need not be periodic. periodic.
Yeah,
That's what I understood.
yeah, that is correct.
To no more point. We
Okay,
can proceed.
all right. So I hope everybody is clear on this question. It is option B, h cross square k square by 2m. Okay, so let's say I have one more exercise for you guys uh, before proceeding to the next question. I think what we should do is psi is e to our I kx plus 4 e to our minus I kx. And our Schrodinger's equation is del 2 psi by del x square plus 2 me upon h cross square psi is 0. So can you substitute this value of psi here in this derivative and here and then find what is e? It should come out to be the same. K square equals to, sorry, e equals to h cross square k square by 2m. So try this for a minute. Try to find what is del psi by del x and del 2 psi by del x square. Then let's see what do we get.
Yes, sir, got it.
Okay, what is del psi by del x? It will be ikx minus 4 ik e to power minus ikx, right?
Yes.
And del 2 psi by del x square will be I square k power ikx plus 4 I square k e to power minus ikx. If I take, let's say,
K square.
I square, yeah, k square, I square k square common ikx plus 4 e to power minus ikx I square is -1, this is minus k square, and this is psi. Del 2 psi by del x square is minus k square psi. So if I substitute in this equation, minus k square psi plus 2me by x plus square psi equals to 0. So this will simply give me k square is 2me by x plus square, or e is x plus square k square by 2m. Okay, let's say to be integral multiple of wavelength it needs to be periodic, but will it be in the allowed energy gap? Okay, so Michaela, maybe we can discuss this at the end of the class. I'm not sure you exactly get your point, but let's discuss it at the end of the class. Okay, so let's go to the next question. So the question is, silicon has a diamond cubic lattice structure with a lattice constant of 5.43 angstroms. So it's not visible maybe. Okay. The silicon crystal is formed by periodic repetition of unit cells in XYZ direction. So this is a unit cell. In each unit cell, 8 atoms at the corners are shared by 8 adjacent cells. So these are the 8 atoms at the corners, right? So they'll be shared by 8 similar, like 8 cubes will share this one corner atom, like here, and cubes will be at top also. So this particular atom will be shared by 8, 8, and the corner atoms are contribute 1/8 of a unit cell. So we have 8 of these corner atoms, 2, 3, 4, 5, 6, 7, and 8. And these 8 contribute shared by 8. So in one unit cell, it would be 8 into 1 by 8, their contribution. 6 atoms at the center of each phase is shared by 2 adjacent unit cells. So this atom at the space will be shared by this cube as well as a cube above. So and there are 6 such phase centers. So it will be plus 6 into 1 by 2. And lastly, 4 atoms within the body of unit cell contribute fully. And there are 4 atoms inside the unit cell, 1, 2, 3, and 4, which contribute completely, plus 4. So in total, in one unit cell, you have 8 atoms. Sorry, You should write it. 8 into 1 by 8 is 1 plus 6 into 1 by 2 is 3 plus 4, which is 8 atoms in one unit cell of silicon. Okay, now the question is determine the density of the atoms in atom number of atoms per centimeter cube. So we know this length of the unit cell A is 5.43 angstrom, or you can write it as 0.543 nanometer, and centimeter it will be 0.543 10 to the minus 7 centimeter, and volume of unit cell will be A cube, right? So equals to 0.543 into 10 to the minus 7 cube centimeter cube. And when we do this math, we get 1.6 into 10 to the power 22 centimeter cube. Sorry, minus 22 centimeter cube. This is the volume of one unit cell, A cube. So what will be density? The number of atoms upon volume. This will be 8 upon 1.6 into 10 to the power minus 22 centimeter cube. So what will be the density among these options?
5 into 10 to power 22.
It will be 5 into 10 to the power 22 per centimeter cube. Okay, so is there any doubt in this question? Okay, great. So let us move on to the next one. So read this question. Let's see how to solve this.
So 1.1 nanometer.
Okay, Are there any other answers? Okay, did anyone get some answer? Okay, so let us try to solve this one. Question is, consider an electron confined in an infinite square well of width 1 nanometer. So we have an infinite square well until infinity, and its width, this is 1 nanometer. If an electron undergoes a transition from first excited state n equal to 2 to ground state n equal to 1, it emits a photon. So there are two states here, equal to 1, n equals to 2, and an electron is transiting from here to here and emitting a photon. Calculate the wavelength of the photon emitted during the same transition. Okay, so we are emitting a photon here. So basically what we need to do, we need to find the energy difference between these two to find the wavelength of the photon. For photon, energy is hc by lambda, right? This is a standard relation between wavelength and energy for photon, hc by lambda, and so lambda will be hc by e. We have to find lambda of this photon. We need to find hc by e.
Sir,
For
I'm
this,
getting D part.
you are getting B part, D part. Okay, 1.1 micrometer. Okay, so here lambda of this photon will be hc by E2 minus E1, right? So that, and for infinite potential well, so if you see the solution of the Schrodinger's equation, we get this energy relation equals to n plus square pi square h cross square upon 2 ml square. So E2 will be 4.
Option C is correct, sir.
No, it is not. Okay, so E2 is, we will put n equals to 2, 4 pi square h cross square upon 2 ml square. E1 is 4, E1 sorry will be pi square h cross square upon 2 ml square. So your delta E, let me call it HC by delta E. Delta E is 3 pi square h cross square upon 2 ml square. Lambda will be HC upon 3 pi square h cross square upon 2 ml square. I will replace this h cross square by h crosses h upon 2 pi. So h2 h square upon 4 pi square will cancel. So we will get lambda equals to hc. So this h and h square will also cancel. We'll get 2ml square to 4c upon 3h, and L is 1 nanometer. Okay, so we substitute everything. It will be 2 into 9.1 into 10 to the power minus 31 into L will be 1 into 10 to the power minus 9 whole square. 4 into 3 into 10 to the power 8 is C. 3 into 1626 into 10 to the power minus 54. What I would get is 1.1 into 10 to the power minus 6, which is 1.1 micrometer, which is option D. Okay, so those who are getting 1.1 nanometer, can you tell me where are you going wrong?
No, sir. This,
Adi Kamle, you got 1.1 nanometer, right?
Sir, I think I am wrong in calculation.
Okay, so please take care of these units very well. So if you're taking this C, H, and M in like NK system, you need to take L also in meters. So be very mindful about these because like you see in this question, all the values are same, only units are different. So they know you will be confused in units only. So be very careful about these units. So anyways, so the few important things I'll highlight in this question is one is this for infinite potential well, this is the energy relation. Another thing is this Hc by lambda is E. It's like a standard relation. Okay, any doubts in this?
no, sir.
All right, great. See the next one. There are two semiconducting materials with energy band gaps. EGA is zero point 0.7 electron volt and EGB is 1.4 electron volt. Which of the following is true regarding the probability Pi of electron hole pair generation at the same temperature T? So T is temperature. So it's a very simple question.
For C part,
EB laser equal to PA.
Sorry, can you repeat?
Yeah, it should be C.
EB,
C.
It should be C.
yes, sir.
The probability at B should be less than probability at A.
Right. C. So this simply based on the relation proportional to G by KT, right? Or you can even intuitively think maybe uh, there are two band gaps, EA and EB. When same energy is given to the electrons in valence band of both of these, which barrier would be easier to cross, right? The smaller barrier would be easier to cross. So the probability of electron hole pair generation in A would be much greater than PB, or in this case, yeah, PB less than PA. Right? This is very intuitive. Since EG B is greater than EGA, PB is less than PA. Okay, is this portion clear to all?
Yes, yes.
Okay,
Yes, sir.
next one is a very interesting question. Consider two semiconductor materials, germanium with energy bandgap of 0.7 electron volts and sapphire with energy bandgap of 9.9 electron volts. Each material will be transparent for visible light of wavelength 400 nanometers. So you have germanium's bandgap 0.7 electron volts and sapphires, let me call it ES, is 9.9 electron volt. Which material will be transparent to visible light for wavelength of lambda 400 nanometer? Which one will be transparent? Think about it. Let's solve it in a way.
Sir, B part.
Yeah, it will be B. Why B?
sir, because the energy of light is coming to be about 3 electron volt, so it is less less than that of less than the energy band gap of sapphire. So it will not be able to excite the electron and thus will not be absorbed by sapphire.
So what you said is right. if you see the energy of this photon is c by lambda, it will be like in terms of it's only 1.24 by lambda, lambda is in micrometer volts. They put it 1.24 by 400 will be 0.4. It will be 3.1 electron volts. So the energy of the incoming photon is 3.1 electron volt. So if Eg is less than 3.1 electron volt, it will excite electron hole pair and so it will generate electron hole pair and absorb the energy. If Eg is greater than 3.1 electron volt, it will transmit. And if it transmits, that means the material will be transparent to this wavelength. So it will be sapphire. Why? Because sapphire has 9.9 electron volt, which is greater than 3.1 of the light. Okay, I hope this is clear to all. Okay, let's move on to the next one. Identify which of the following statements is true from the given figure. Okay, so before that, can anyone tell me what is wrong with this picture? Before going to the question itself, let's talk about this a minute. What is wrong with this picture here? Crystal momentum is different. What does that mean here? Like, why is, what do you mean? Like, how is that wrong? Anybody else? What is wrong with this picture? K is wrong. Adi, can you?
Conduction band and valence band.
Yeah, what is wrong in conduction band and valence band? Sanjeev, can you explain what is wrong?
So 1.12 electron volt.
Sorry?
This is not uh, actually right in the 1.42 electron volt. Valence band and conduction band is the same line.
Okay.
So incorrect is here valence band and conduction band is not the same line.
So that just means this is a direct band gap and this is not in, this is an indirect band gap, right?
What I think it's a confusion between electron and hole. So this maxima and minima should be opposites, mirror images.
Okay. So no. So all of you are incorrect. So everything else in this picture is fine except one thing, that is this representation of this electrons and holes, right? So can electrons exist like this or can holes exist like this? Okay, I think you guys are like missing what I'm trying to ask, so I'll get straight to it. So, okay, so when you all solve the Schrodinger equation, right, you get some EK relation, E equals to n square, pi square, h cross square, by 2, L square, mn square, sorry. This is for like infinite potential well. So your EK is like something like this, right? And for finite potential well, these are like or even bit closer. So the whole point is this in this E and K, there are only these states which are allowed, right? Only this energy and this momentum, at this momentum, let's say at this particular momentum K1, only this particular energy is allowed. At this particular momentum K2, only this particular energy is allowed, right? So this was the whole point of solving the Schrodinger equation. So what they have shown here is this is actually the allowed level. This whole thing is allowed. Anything on this line is allowed. But these things are not allowed, right? There's no allowed energy here. So rather than here, your electrons would be somewhere on this line. This is not a bucket, right? You're not filling the electrons in this bucket. Your electrons would be on this, your states, allowed states will be on this line, not anywhere else. It cannot exist here, it cannot exist here. It was the whole point of drawing this line, right? Only this particular energy is allowed for this momentum. Am I making sense?
Yes, sir.
Yes, sir.
Right? So this is a very incorrect figure. It is often given in various books. So be very mindful of it. This part is not allowed. This is not allowed. It is not a bucket. And we generally confuse it with something like this. It will be allowed here, 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 or on the line. Okay. So it is not related to this question, but since we had this figure, okay. So now let's get back to our question. The question is, which of the following are true? Okay, so silicon is an indirect bandgap material, and gallium arsenide is a direct bandgap material. Okay, this is for silicon. This is for gallium arsenide. We saw this is indirect bandgap, direct bandgap. Indirect direct bandgap just means this, like if this momentum at the same K value, you have the valence band uh, maxima and conduction band minima. That means it is a direct bandgap. If they are not at the same value, same K value, that means they are indirect bandgap. Momentum is conserved in indirect bandgap material. Silicon is a direct bandgap material. Gallium arsenide is indirect. Momentum is conserved in direct. So, okay, first one is true for sure. Second one is false for sure. So, third one is false. What is second one and what is last one? Which among them is true?
1 and 4 are correct.
Right. This is true and this is false.
So option C.
Right. So we can see directly here. If an electron goes from here to here, oh sorry, electron goes from here to here, it is traveling in the same momentum state. E is not changing. So momentum is conserved in direct bandgap. Whereas here, if it has to go from here to here, it needs to change its momentum. The momentum here, K1 and here at K0 are not the same, right? So the correct answer is 1 and 4 are correct. Option C.
Yes, sir, got it.
Okay, great.
Sir,
Yes.
when we solved the Schrodinger wave equation, we found that the vertex lied at k is equal to 0, but in silicon that is not true. What is the reason for that?
While solving, did we consider it like we are solving it specifically for uh, silicon?
No, sir.
Okay. So what you see is like k equals to 0 or k equal to what these numbers are just relative here, right? This is just a nomenclature. Wherever this valence band maxima lies, we call it the gamma point. And toward this direction is the x side. This direction is the L side. So this is just a relative nomenclature. It does not matter. These numbers don't matter here. Uh, the only thing to important here is like they are both are at different k values.
Sir, but that the solution to Schrodinger wave equation represents that at minimum momentum there will be minimum energy. But here it is not the case.
At minimum momentum, there will be minimum energy. Okay. Okay. So what do we solve in Schrodinger's equation is what we just solve. Okay. Right. So what we are solving it like we are solving a few cases. One is like infinite, uh, sorry, free particle. where V is zero. Another one we are solving is V is infinite, infinite potential well. Third one, we may solve finite potential when V is equals to finite. So whatever solution you have seen till now are for like this free particle or infinite potential well, right? And that is not a true representation of the silicon atom. What happens in a silicon atom is like there are multiple atoms close to each other in some line, right? And there is some potential uh, barrier between the two. Like this is how the potential well is formed, something like this. So it is like a uh, periodic potential well. So their different wave functions overlap with with each other and interact with each other to finally give us this band structure. Okay, and this is also like this is not a complete picture. Due to the periodicity, basically what we do is like uh, we consider only between uh, pi by 2, pi by pi by l. Whatever is coming in between, we just take this and then with some periodic conditions, we like overlap the entire thing in between onto each other. That is how we get this final band structure. So the whole point is like it is not that simple. We are not directly solving for the infinite potential that we solve is not a true representative of silicon. This equation this equation is not a true representative for silicon atom, and there are multiple things at play here. And this is just again a representation, right? This is I just said this is a gamma point. I never said this is zero. This is X point. This is L point. We don't know what the exactly momentum value is there. What value of momentum is there. These are just relative positions,
Okay.
right? This gamma does not mean it is zero. Okay, so if you are interested in learning this, there is a book called um, Advanced Semiconductor Fundamentals, something like that, by author name is Robert F. I think I may be wrong in the spelling, but I think in the first or second chapter of this book, you can find exactly like how this band structure is formed, and they'll explain from starting from this uh, free particle and infinite potential well till how do we reach here. So if anybody is interested, they can go through it, but it's not a like hard requirement for this course. But for your curiosity, who is interested, please read the first or second chapter of this book. But basically, what the similar things is done, we place multiple atoms side by side and solve some kind of finite potential well equation for it to reach here. And it is not an easy task. It is a very like, complex equation. Even solving for a simple finite well is not easy. If you would have tried, finite well solving is not easy. Infinite well we can easily solve to here, but finite well is difficult. Okay, anything else here?
No, sir.
Okay. Cutoff wavelength in micrometer of the light that can be used for intrinsic excitation of semiconductor material or band gap 1.1 electron volt. So basically what they're asking is the band gap is 1.1 electron volt. What is the energy required for transferring electron from here to here? Not energy, the wavelength of the incoming light. It should be the lambda. Okay. B is correct. So we just saw this right now. E is hc by lambda, and for photon, if I substitute the values, I get E is 1.24 by lambda, where lambda is in micrometer, and this E is in electron volt. So, so lambda in micrometer 1.24 upon E in electron volt, 1.24 upon 1.1 is 1.125 micrometer. Simple question.
Okay, sir.
Okay, so let's go to the last question for today. Okay, so forget about this word recoil. The momentum of an atom Pa when it emits an infrared photon of wavelength 1500 nanometer is okay Pa, and it is Pb when it emits wavelength 500 nanometer. What is the ratio of Pa by Pb? Pa by Pb, you have to find uh, lambda A is 1500, lambda B is 500 nanometer. Right. C is the answer.
Option C. Yeah.
So
Yes, sir.
lambda is h upon p. So lambda A by lambda B, or you can write PA by PB will be lambda B by lambda A, which is 500 by 1500, which is 1 by 3. Right? Okay, so these are all the questions I had. So if you have any doubts, please feel free to ask, else you may leave the session or you can close the session.
Sir, why is the EG of germanium lesser than silicon?
Why is the EG of germanium lesser than silicon? Okay. Uh, so I could say it's simply a material property, but some inference could be like germanium is a much bigger atom compared to silicon, right? So, uh, it could be easier to like to displace an electron from germanium or excite an electron from germanium because it has lesser, uh, you can say, attractive force from the nucleus compared to silicon, which is tightly bound in an uh, due to, yeah, I think simply it's because germanium is a bigger atom.
Sir, one more question. Like we studied that if we have an incident photon of a wavelength that can excite the electron from the valence band to the conduction band, then that is absorbed.
Yeah.
So according to this logic, all the metals should be black in color because they have very less uh, band gap, so they can absorb all the light. But we see that metals are of like silverish color or grayish color.
Okay. Interesting question. Uh, okay. So, yeah. Okay, what would be the wavelength of that color? Silver or gray? Let's check.
The silicon would inherently appear black for the same reason as it was mentioned in the question.
Okay, so this particular question was only for this particular wavelength, 400 nanometer, right? Our visible spectrum is much wider. This was just for a 400 nanometer wavelength. So it was uh, only for this particular wavelength, sapphire would not absorb it. So don't confuse like it is like representing the entire spectrum and everything is transparent. It's not the case.
And for band gaps less than 3.1 electron volt, it would be a range of energy levels from valence to conduction band. So then it should start from black and would- and would go to different colors as you
No, no, okay, then you are
go
confused. We
closer
are
to
talking, no,
3.1.
we are only talking about this particular uh, wavelength, right? So whatever this color, let's say this color is blue for this color is blue corresponding to 400 nanometer. Let's assume that. So what it means is below 3.1, oh, sorry, below 3.1, this wavelength, this light will be absorbed, or you will not see any blue hint. But above 3.1, this this light will be transmitted or reflected. So there you could see the blue. It just means like this particular wavelength. It may be
Right,
like
right.
after this, whatever wavelengths are greater than this, they could also be like contribute to make your final color. But we cannot say like it is black or something. Like, no. It just means like this particular wavelength of light is transmitted or absorbed. It is much more complex than this. It's very simple representation. We are only talking about one 400 nanometer length. Let's say for 1.12 electron volt of silicon, uh, what is the required wavelength? Right? Okay, let's just consider it to same to be 1.24. Uh, let's say silicon's EG is 1.24. So lambda will be 1.24 by 1.24 is 1 micrometer. That is 1000 nanometer, right? So whatever wavelength which is lesser than 1000 nanometer, only those will be absorbed. Whatever wavelength greater than 1000 nanometer will be reflected. Does this make sense?
Will pass through.
Yeah. Pass through or reflect, I don't know what to call it. It just it won't be absorbed. Electron hole pairs. It will not consume that wavelength. Either it will like reflect it or I cannot say what pass through, but it can reflect it. Okay, so what was the question? Why metals are gray? Right, it was the question.
Sir, I have a little bit different doubt.
Yeah.
In the next question, where we showed the momentum graphs and all that.
Yeah.
So if there are multiple momentum bands in the conduction region, so will it cause any effect to change in material properties? Something?
When there are multiple momentum, what do you mean? Like
If there are
what's
multiple bands in
yeah.
conduction band or
Okay.
valence region,
Yeah.
uh, So will it cause any changes in material if they are overlapping or crossing each other?
Yeah, definitely. So this is definitely a material property, right? So basically, how do they arise is again related to uh, how is their crystal structure, right? So crystal structure is defined mainly by two things. One is their unit cell, second is their interatomic, this lattice constant. So any change in a particular combination of this should give you ideally a unique set of uh, band structure. So if anything is changing in this band structure, so basically let's say you still have silicon, but you try to compress the silicon or you apply some stress on it so that its A changes or its interatomic distance changes. Then your conduction band and valence band change. They come closer or they go far apart. So this happens. This is very actively used in uh, transistor technology where we apply some kind of particular strain in the silicon so that we can increase or decrease the band gap or change uh, the band structure to get like higher mobility or whatever to our purpose. So yeah, your question basically is like if there are multiple bands. So there usually are multiple bands. It's not like just this picture. So if I just show you, uh, try to find band structure of silicon. So you see, it is not like it has only this uh, one curve. It has lot of curves here, and they are like sub bands or satellite bands for it. So there are always these many bands. It's not a very simplistic pictures, and yeah, it matters. Like every band's position matters. Their distribution matters. If they are coming closer or far apart, that means like the density of states in a particular volume is changing. The number of allowed levels for electrons is changing. So yeah, that does change the material properties.
Yes, sir.
Okay. Was there any other question? Thank you, Shujan. Okay, so that about that question about the gray metal, I'm not sure. Uh, Maybe there is something else at play for that because for metals like band gap is zero, right? So this particular theory does not. I don't think that holds true for it. It should apply. Like there should be something else happening there, like maybe some electron configuration which gets excited and uh, de-excited, which emits some radiation or like allows to absorb some particular wavelength and does not allow some other. So like it is much more complex than this. And yeah, maybe this is true only for semiconductors or like have materials which have a valid band gap. But since metals do not have any band gap, the band gap is like very close to zero at room temperature. So there should be some other consideration, not just this.
So on a second thought, I also think that when they'll absorb the uh, energy, then also they'll emit that energy also. So that might also be causing the color.
Yeah, that is true, but again, that again depends. Like uh, mm, that could be true, but again, I'm not sure. I cannot quantitatively say. So
And
I'll
but
read
in the
about it. Yeah.
case of metals, there is no valence band. So there is no point that it will be transparent to any light. So there is completely different phenomena in case of metals and in the case of semiconductors. This is what I understood.
Yeah, that is true. We are just trying to understand like why there is like color in metals. Like what is the causing factor then? Not this, then what?
Sir, another question I wanted to ask about Fermi energy. Like, we did that graph of energy of
Hmm.
electrons.
Yeah.
So in that we got to know that at Fermi energy, the probability to find electron is zero point 0.5.
Okay.
And
Yes.
so, but we also know that the electron can be either in the valence band or conduction band.
Yeah.
So, but Fermi level is between those two. So how can we find anything there?
Okay. So Fermi energy is not a is a hypothetical energy, right? It's not uh, it is not a real energy. So uh, I understand
So,
what you're
but
coming
exactly
from.
like in that graph, at the energy levels between the two bands, the probability should be zero at all points. But it is a continuous graph, like you have drawn.
Okay, so I'll think about it, what you're trying to say, I understand. So I think it is in the next week's lecture. I'll touch this topic. I I'll talk in detail about this. Okay?
Oh, yes, sir.
Yes, sir.
Thank you. Thanks a lot.
Okay. Bye guys. Thank you.
Thank you,
Thank you,
sir.
sir.
Yeah.
Thank you.